in the infinite expanse of the dataverse. Existence is defined by context. You are not who you say you are. You are who you stand next to. Initiate the proximity protocol. Let the universe tell us its story based on where it drifted. We don't need a map to find the truth. We just need neighbors. Scan for the nearest points, and let the light reveal the stranger's name. Initiate the Euclidean scan now, because the unknown doesn't exist in a vacuum. It exists in the gaps between what we already know. Reach out and measure the void. I want every dimension accounted for: latitude, intensity, frequency, vector. If it has a value, I want it mapped. Watch the screen as the distance formula fires. D equals the square root of the sum of square differences. It's a mathematical bridge connecting this stranger to our collective archive. System, lock the K value to 5. I want a council, not a crowd. Identify the 5 nearest souls in this infinite dark to tell us exactly who this anomaly is. Proximity established. Accessing the primary training module, the Iris archives. This is the perfect proving ground for the algorithm. We are analyzing 150 biological signals, divided into 3 distinct signatures. Class 0, the red setosa. Class 1, the green versicolor. Class 2, the blue virginica, 50 samples each, perfectly balanced. But how do we map them? Through 4 specific dimensions: sepal length, sepal width, petal length, and petal width. Watch as the raw data populates the matrix. These aren't just numbers, they are fixed points in space waiting to be classified. This data set is the ideal test for the proximity protocol because the separation is clear. The dimensions are low, and the distance patterns are undeniable. If you want to master the nearest neighbor, you start here. Synchronizing with the neural grid. Welcome to the vector frontier. Before us lies the iris topology, 150 data signatures suspended in a 3-dimensional manifold. Notice the clusters: the red setosa, the green versicolor, and the blue virginica, each a distinct colony in this geometric expanse. Watch the query point drifting through the vacuum. As it moves, the proximity protocol is active in real time, calculating Euclidean distances across every axis. Look closer. The 5 yellow filaments are the council of K, reaching out to the nearest neighbors to claim this anomaly for their own. The system is scanning for the majority. Is it 2 against 3, or a unanimous takeover? The filaments pulse as the vote is tallied. In this space, identity is not a choice. It is an inheritance. Proximity confirmed. The anomaly is no longer unknown. It has found its home. Target classified. We are initiating the high-dimensional stress test. Watch as we move from the stable 2-dimensional grid into the uncharted territory of hyperspace. At 2 dimensions, the topology is dense, the clusters are distinct, and the nearest neighbors are truly nearby. But as the dimension count climbs toward 10, the architecture of reality begins to warp. This is the curse of dimensionality. Notice the query point. It is pulsing with uncertainty as the data points around it become exponentially sparse. The yellow filaments are stretching thinner, losing their grip on identity. In this void, every point is becoming equally distant from every other point. When everything is a stranger, distance loses its meaning. and the Council of K falls silent. The protocol has failed. We begin with a single observation, labeled X, floating alone in uncertainty, not as one value, but as a collection of features written as x1 through xn, each describing a different aspect of the same reality. In front of us lie multiple possible classes, C1 through CK, and the task of classification is to decide which of these worlds best explains the observation we have just received. The question we are trying to answer is precise and profound. Given this observation X, what is the probability that it belongs to each class? This probability is known as the posterior, and it is governed by one of the most important ideas in probability theory, Bayes' Theorem. Bayes' Theorem tells us that our belief after seeing the data is shaped by three forces. The likelihood, which measures how well a class explains the observed features, the prior, which captures what we believed about that class before seeing any data at all, and the evidence, which acts as a normalization factor, ensuring that all probabilities remain consistent. For the purpose of classification, this evidence is the same across all classes, so we can safely ignore it and focus on what truly matters. Likelihood times prior. The prior represents how common each class is in the real world, while the likelihood answers a deeper question. If this class were true, how likely would we be to observe features like these? Unfortunately, computing the full joint likelihood of all features together is extremely difficult. So naive Bayes makes a bold, simplifying assumption. Given the class, each feature behaves independently of the others. This single assumption transforms an intractable joint probability into a clean product of individual likelihoods, turning complexity into structure. When we combine this product with the prior, we arrive at the naive Bayes classifier, which chooses the class with the highest resulting score. In practice, multiplying many small probabilities can cause numerical instability, so we move into log space, where products become sums while preserving the exact same decision. And although the independence assumption is rarely true in the real world, this deceptively simple model remains fast, elegant, and remarkably effective. Let's understand all of these complex mathematical ideas using a simple, classical example that everyone recognizes. An email arriving in your inbox. A new message appears, containing just a few words, yet hiding an important decision. Should this email be trusted, or should it be marked as spam? In our model, there are only two possible explanations, spam or not spam, and our goal is to compute a single quantity, the probability that this specific email is spam, given the words it contains. To begin, we step back and look at what we already know from past data. From a large collection of previously labeled emails, we observe that spam is more common, giving us our prior beliefs. A 70% chance for spam and 30% for not spam before reading a single word of the message. Now we examine the email itself, extracting individual features from its content, the words win, money, and free, because to the model, an email is nothing more than a collection of measurable features. From the training data, we calculate how often each of these words appears in spam emails and how rarely they appear in legitimate ones, revealing a dramatic contrast between the two classes. At this point, naive Bayes makes its defining move. It assumes that given the class, each word contributes evidence independently of the others. This single assumption allows us to replace an intractable joint probability with a simple product of likelihoods. We now compute a score for each class by multiplying the prior probability with the likelihood of every observed word. For spam, the score grows large and confident, while for not spam, it collapses to an almost negligible value. When we compare these scores, the outcome becomes unavoidable. The email is classified as spam. Finally, because multiplying many small probabilities can cause numerical instability, we move into log space, where products become sums while the decision itself remains unchanged. And with that, naive Bayes reaches its conclusion, not through intuition or handcrafted rules, but by letting data, probability, and a simple assumption speak for themselves. Let's understand naive Bayes using a simple, classical, and very real example: employee salary classification. Instead of abstract equations, we'll work with people, jobs, and experience. We begin by defining the feature space in which our model operates. Each employee is described using discrete features such as education level, years of experience, and job type. Together, these features form a structured space where every point represents a possible employee profile. From historical data, training samples populate this space, revealing clear patterns. Employees with high salaries tend to cluster in certain regions, while lower salaries dominate others. Before looking at any individual employee, the model forms its initial belief known as the prior probability. Based on past data, some salary outcomes are simply more common than others. Now, a new employee arrives, someone with a master's degree, senior-level experience, and a technical role. Our task is to determine which salary class best explains this combination of features. Naive Bayes approaches this question by combining prior belief with feature-level evidence. It makes a simplifying but powerful assumption. Given the salary class, each feature contributes independently to the final decision. This allows the model to compute a score for each class by multiplying the prior probability with the likelihood of observing each feature under that class. The class with the highest resulting score becomes the prediction. In this case, the evidence aligns strongly with the high salary region, leading to a confident classification. This is the essence of categorical naive Bayes. Simple assumptions, discrete probabilities, and decisions driven entirely by data Real-world data is inherently noisy, uncertain, and incomplete, and any meaningful learning method must operate despite this messiness rather than ignoring it. Linear regression begins by seeking a simple structure, a single line, that can summarize an overall trend without claiming perfect accuracy. This line is not discovered but assumed, defined by parameters that control its slope and position, forming a family of possible models. Data arrives through measurement, one observation at a time, each carrying its own variation, and the model must account for this imperfection. Errors emerge as the visible consequences of our assumptions, measured as distances between predictions and reality. Learning, then, becomes an optimization problem, moving through parameter space to reduce these errors. By following the geometry of the error surface and descending toward its minimum, the model steadily improves until no further meaningful reduction is possible. This process, defining a model, measuring error, and minimizing it, is the essence of linear regression. Let's understand the math behind linear regression by starting with its simplest idea: modeling a relationship between two variables using a straight line. Real-world data is noisy, but even in the presence of randomness, an overall trend often exists. Linear regression captures this trend using the equation y equals mx plus b, where the slope m controls how rapidly the output changes with the input, and the intercept b sets the baseline value when the input is 0. By adjusting these two parameters, we generate different candidate lines, each representing a possible explanation of the data, and our task is to identify the one that best describes the underlying pattern. Once a line is chosen, each data point produces an error, defined as the vertical difference between the observed value and the value predicted by the model. These errors, called residuals, measure how wrong the model is at individual points. To evaluate the model as a whole, we combine all residuals into a single quantity known as the sum of squared errors. Squaring the errors prevents positive and negative deviations from canceling and ensures that larger mistakes are penalized more heavily. Linear regression is therefore defined by a clear objective: finding the line that minimizes this total squared error. To find the line that minimizes error, we treat linear regression as an optimization problem. By expressing the total squared error as a function of the slope and intercept, calculus allows us to locate its minimum by setting partial derivatives to 0. This analytical solution has a clear geometric meaning. The optimal line always passes through the centroid of the data, defined by the mean of the inputs and the mean of the outputs. Rotating the line around this central point changes how errors balance across the data, and the best slope emerges when this balance is minimized. In this way, calculus and geometry describe the same solution from different perspectives. With a concrete data set, linear regression can be computed step by first calculating the means of the inputs and outputs, then using their deviations to determine the slope, and finally computing the intercept. This produces a specific equation that best fits the observed data. Once the model is obtained, its quality must be evaluated. The R-squared metric measures how much of the total variation in the data is explained by the regression line, comparing the model's error to the variability present before fitting any line. A higher R-squared value indicates that the model captures a larger fraction of the underlying pattern. When analytical solutions become impractical due to large data sets or complex models, gradient descent provides an iterative way to learn the parameters of linear regression. Instead of solving in one step, the model repeatedly updates the slope and intercept in the direction that reduces error, gradually moving toward the minimum of the loss function. Together, these ideas complete the framework of linear regression: a simple linear model, an objective defined by squared error, solutions obtained either analytically or iteratively, and evaluation through measures like R-squared. Despite its simplicity, this framework forms the foundation upon which much of modern machine learning is built. We begin with a simple and intuitive problem: understanding how house prices relate to house size. Each point represents a real house, with size measured in hundreds of square feet and price measured in hundreds of thousands of dollars. When we plot this data, we observe a scattered pattern that reflects natural variability, yet a clear upward trend begins to emerge. This raises a fundamental question at the heart of linear regression. Can a simple mathematical model capture the relationship between size and price, despite the noise in real-world data? We represent this relationship with a straight line defined by a slope and an intercept. The slope quantifies how much the house price is expected to increase for each additional unit of size, while the intercept represents the baseline price before size has any effect. Since real data is never perfectly linear, the line will not pass through every point. We therefore measure error as the difference between the actual price and the price predicted by the model, and evaluate the overall fit by minimizing the total squared error across all houses. This optimization yields the best fit equation, and its effectiveness is summarized using R-squared, which tells us how much of the variation in house prices is explained by size. With this model established, we can make informed predictions for new houses, completing the full progression from raw data to mathematical insight. Some problems are not about predicting a number, but about making a decision. In many real situations, outcomes fall into categories: yes or no, true or false, one class or another. When we look at such data, we often see two overlapping groups with no clean separation between them. If we try to force a straight line to solve this kind of problem, it struggles, producing ambiguous and misleading results. The line can assign a score, but that score alone does not tell us how confident the decision should be. What we really want is a measure of confidence that is bounded and interpretable, not unreasonably large or small. By transforming raw scores into a smooth notion of confidence and applying a decision threshold, we move from prediction to classification. Finally, replacing hard boundaries with smooth transitions allows uncertainty to be handled naturally. This shift from values to probabilities and from rigid decisions to soft boundaries reveals the need for a different model, setting the stage for logistic regression. Let's try to understand the mathematics behind logistic regression. In classification tasks, outcomes belong to discrete categories such as spam or not spam, disease or healthy, fraud or legitimate. These problems require probabilities between 0 and 1. When we try to apply linear regression, it produces outputs that fall outside this range, making them impossible to interpret as probabilities. Linear regression is also highly sensitive to outliers and provides no natural way to decide where one class ends and another begins. The sigmoid function is the core of logistic regression. It takes any real-valued input and maps it to a number strictly between 0 and 1. This makes it suitable for modeling probabilities. The input, often denoted as z, can be positive or negative without restriction, but the output is always bounded. When z is 0, the sigmoid output is 1/2. As z becomes large and positive, the output approaches 1, and as z becomes large and negative, the output approaches 0. This smooth S-shaped curve provides a continuous transition between classes. An important property of the sigmoid function is that its derivative depends only on its output, which makes gradient-based optimization efficient. For these reasons, the sigmoid function is a natural choice for logistic regression. In logistic regression, the model output is interpreted as a probability. The sigmoid function maps any input to a value between 0 and 1, which we read as the probability that an observation belongs to class 1. For binary classification, the probability of class 0 is simply 1 minus this value, so the two always sum to 1. While probabilities are intuitive, they are not well suited for linear modeling. To address this, we express probability in terms of odds, defined as the ratio of success to failure. Odds range from 0 to infinity and are not symmetric, which makes them difficult to model directly. Taking the logarithm of the odds solves this problem. The log odds, or logit, range from negative to positive infinity and are symmetric around 0. Logistic regression models this log odds value as a linear function of the inputs, and the sigmoid function then converts it back into a probability. This connection explains how logistic regression combines linear models with probabilistic interpretation. Logistic regression begins with a familiar idea, a linear combination of input features and parameters, just like linear regression. This linear score is then passed through the sigmoid function, which converts it into a probability between 0 and 1. The resulting equation defines the probability that an input belongs to class 1. To learn the parameters of this model, we use maximum likelihood estimation. The idea is to choose parameters that make the observed labels most probable under the model. For each data point, the likelihood depends on whether the predicted probability aligns with the true label. By multiplying these likelihoods across all data points and taking the logarithm, we obtain the log likelihood, which is easier to optimize. Logistic regression has no closed-form solution, so we find the parameters by maximizing the log likelihood using iterative methods such as gradient descent. This completes the mathematical formulation and training process of logistic regression. In logistic regression, learning the model parameters is an optimization problem. After defining the model and its probabilistic output, we must decide how to measure how well the model fits the data. Mean squared error, which is commonly used in linear regression, is not suitable here. When combined with the sigmoid function, it leads to a non-convex objective and unstable optimization. Instead, logistic regression uses log loss, also called binary cross-entropy. This loss function is derived from probability theory and measures how likely the observed labels are under the model's predicted probabilities. It penalizes confident but incorrect predictions strongly and produces a smooth, convex cost surface with a single global minimum. To minimize this cost function, logistic regression relies on gradient descent. There is no closed-form solution for the optimal parameters, so they must be learned iteratively. Gradient descent begins with an initial guess for the parameters and repeatedly updates them by computing the gradient of the cost function. The gradient indicates the direction in which the cost increases most rapidly, so updating the parameters in the opposite direction reduces error. With a suitable learning rate, this process steadily improves the model until the parameters converge to values that minimize the cost. Once the parameters are learned, the model defines a decision rule. Logistic regression outputs probabilities, but classification requires a discrete decision. The decision boundary is defined by the set of points where the predicted probability equals 1/2. This boundary separates the feature space into two regions corresponding to the two classes. Adjusting the probability threshold shifts the decision boundary, allowing control over classification behavior. Together, the cost function, gradient descent, and decision boundary explain how logistic regression is trained and applied to classification problems. Let's start with a simple question. Can we predict whether a student will pass or fail an exam based on the number of hours studied? Each data point represents one student, with hours studied as the input and the outcome as either pass or fail. When we visualize this data, a pattern begins to appear. Students who study more are more likely to pass, but the outcomes remain binary. If we try to apply a straight line to this problem, it quickly fails, producing predictions that fall below 0 or above 1, which cannot be interpreted as probabilities. To fix this, we introduce the sigmoid function, which smoothly transforms any linear score into a value between 0 and 1. This allows us to interpret model outputs as probabilities. Logistic regression then learns the parameters of this sigmoid curve by minimizing error using gradient descent, gradually adjusting the model until it best fits the data. Once trained, the model defines a decision boundary at a probability of 50%, separating pass from fail. With this boundary in place, logistic regression turns raw data into clear, interpretable decisions.